Advancements in technology have enabled high quality and granular measurements of ground level conditions from satellites, therefore enabling the use of satellite data to guide electrification planning and energy systems planning. So we, researchers from University of Massachusetts Amherst, RWI, Columbia, and Policy Studies Institute investigated the use of satellite data to detect diesel-powered irrigation for guiding electrification in Ethiopia. My name is Jen Lukuyu, and for this presentation, I will be walking you through what we did, how we collected data, some of our methodology and results, and policy implications. So over the past couple of decades, there have been international financing from development partners to accelerate electricity access in sub-Saharan Africa. A bulk of these funds have gone into the extension of the traditional grid, which has been pretty expensive. A lot of rural electrification projects in sub-Saharan Africa can actually cost well over $1 million to transmit just 1 megawatt of power for a kilometer. I've shown some examples here. We can see a project in Uganda, which costed just over $3 million per kilometer. And so cost recovery for utilities have been challenging because of low revenue collection. So we've seen that even as electricity access rates in sub-Saharan Africa have increased, the consumption per capita still remains stunted and is lagging behind other regions. And so, as I mentioned before, a lot of utilities in sub-Saharan Africa did accelerate rural electrification in the past decade, and we've seen a lot of them requiring bailouts and suffering a lot of losses just because of inadequate revenue generation. And so, very big number of utilities are operating at a major deficit, requiring a lot of subsidies, on average deficit of 12 US cents per kilowatt hour. We actually see only 2 utilities in sub-Saharan Africa are actually profitable, Uganda and Seychelles. And over the past few years, we've been seeing that the number of utilities that are actually not recovering their costs of investment and operating costs increasing. And so what's actually the problem with this? What's happening is then a lot of utilities are charging very high connection charges and tariffs to be able to recover the costs of the investments, which can largely be very out of reach for low-income rural communities. For example, there's some countries that can have as high as 10% of their monthly bill going into just paying electricity bills. And in terms of connection charges, we can see over 200 to 400% of monthly incomes having to be used for connection charges, which again, I say is out of reach for low-income rural communities, which is then hindering them from actually benefiting from electrification. And this is the intent of electrification in the first place. So what's the solution? One solution is to prioritize electrification of areas with a high potential for what I would say sufficient concentrated or anchor demand, which can provide constant and long-term revenue for utilities and other electrification companies. And this is very crucial for the viability of rural electrification projects. So this is not new. Historically, Vietnam was a very successful example of a country that did this. Electrification rates in Vietnam really skyrocketed over the past 30, 40 years. In 1975, they had as low as 2% electricity access among poor households. And electricity access has grown up until 100% just up and as of 2018. But we can see that there was also growth of consumption, and this is because policymakers prioritized electrified areas with high potential for productive use like irrigation. And then in turn, the added revenue that was generated from increased incomes from households was used into electrifying new areas, and this promoted the overall financial viability of rural electrification. And so this model has been adapted by a lot of sub-Saharan African countries that are going through electrification now. One example is Ethiopia. In their national electrification plan, they're targeting universal electricity access by 2030, mainly through grid connections. The aim is to have 96% of connections long-term by extending the grid. And they are specifically prioritizing grid access to areas with a high potential for irrigation and agricultural processing. Currently in Ethiopia, irrigation is a big activity because agriculture underpins the economic growth of Ethiopia. But a lot of current irrigation is done using diesel irrigation pumps. The estimate is about 200,000. The thing is, we just don't know where this diesel irrigation activity is happening. So for this study, we sought to answer one question. Can we use satellite data and machine learning techniques to identify where there is diesel-based irrigation activity in Ethiopia? And this activity can be prioritized for electrification and serve as this anchor load in rural areas that can be beneficial for utilities in terms of revenue generation, but also be beneficial for the communities by creating opportunities for faster electrification. And so we're using two main satellite data sources. Pollution. So pollution, NO2 and carbon monoxide. So nitrogen dioxide and carbon monoxide are two main pollutants from diesel engines. And this can be measured remotely through the Sentinel-5 satellite with a good both spatial and temporal resolution. And we're also leveraging vegetation indices from the Terra Modis satellite. And this measures the greenness and changes in the greenness of vegetation at a temporal resolution of 16 days, spatially at 250 meters. And so our hypothesis is that we can detect diesel-powered irrigation activity by matching the trends in pollution, patterns in pollution, and also vegetation to irrigation seasonality. So when we look at the time when we actually collected data, which is around 2021, early 21. So we looked at the precipitation around that time to identify the dry season. So irrigation tends to happen around the dry season. And so from the data we collected, the data we got for precipitation, we can see that that happened around November of 2020 to early 2021 up to about March. And so we expect irrigation to happen during this time. And this is supported by the data, the ground data we collected. And we saw that from the questions we asked, the farmers, a lot of them said they were irrigating again during this dry season. And so when we look at the differences in pollution from areas we know, and I'll be talking about our ground collection data process a little bit later, but from that ground collection, our ground truth data set, we know where in our sample where diesel irrigation is happening and where non-diesel irrigation is happening. And when we compare the pollution of those two sets of places, we can clearly see during the dry season is when there is an elevated pollution measurement in the diesel irrigated area compared to the non-diesel irrigated areas. And so that is really the trend we are leveraging as a hypothesis for our study. And then we apply a feature-based multivariate time series classification, modified such that we can also incorporate some time constant features. And I will mention a little bit later what those time constant features are. And so we extract features from the time series, the pollution and the vegetation time series trends. And then we use these extracted features combined with the time series features for training our model and doing the predictions and evaluating our model. And so just to back up and talk a little bit about our ground collection, how we collected our ground truth data set. So in early March to April of 2021, we collected about 6,000 plot measurements and locations in the Amhara and Oromia regions of Ethiopia, which is a little bit up northwest, I would say. And some of the information we're collecting from farmers was when they irrigate, what method of irrigation they use, what crops they grow. And we also had a team of enumerators actually pinpoint where the plots were and take measurements. And so from all this data from the different plots, what we did is define a 250-meter resolution grid cell over the study areas that I just mentioned. And so we gave them labels based on the pixels that contained only plots that are within the same class. So those that had only plots that were diesel irrigated, those were fell into the diesel irrigation class, compared to those that say only had plots that were not being irrigated during this time, which fell into the non-irrigation class. And then we defined the features based on our domain knowledge of the factors that would influence our choice of irrigation, as well as other attributes like cultivated land and diesel powered pumps. So like pollution, as I said, vegetation indices, proximity to water, elevation, and human activity measured through population. And so then we compared two approaches, a single ternary classification approach, where we directly classified the ground truth data sets into those three classes. Irrigated with diesel, irrigated but with a non-diesel based pump or method, and then those that had no irrigation activity. And then we compare this to a two-stage binary classification approach, where we first of all had a binary classification of areas that are not irrigated and those that are irrigated, and then build upon this stage by taking areas that have irrigation activity and then classifying them as either diesel or non-diesel. And the benefit of this approach is then that we can build off of models that can more accurately or better predict irrigation activity. And so from our results in the single stage ternary classification approach, we found that it was better detecting non-irrigation activity compared to the other two classes. So if we look at the diesel, both the diesel and non-diesel irrigation classes, we find that a lot of misclassification happens with pixels being classified as non-irrigated. So it was finding it hard to kind of separate the diesel and non-diesel classes when we have the non-irrigated class. And we also considered the Matthews correlation coefficient to check the balance of predictions. And we see that it doesn't deviate too much from the F1 score, which then shows that we are not incorrectly favoring one class over the other. And so this result gave us a good also basis and support for doing the two-stage binary classification approach. And in this case, we found that our k-nearest neighbors classifier was the best performing model, and it's accurately detected, or rather it detected diesel irrigation activity with an F1 score of 90%. And we see a good balance given by the Matthews correlation coefficient. And we see that the diesel class is being classified with a precision of about 91%. And so we took this KNN model and applied it to the entire region of Amhara, which was where we had most of our ground truth sample collected. And we found that our model predicts that 20% of irrigation activity in the Amhara region is diesel powered, and it largely takes place in the western part of the region. So just a few caveats and something that is a basis for future work. One, as we saw earlier when I talked through the number of pixels we had, we found that our model was trained on quite a small data set. And so which presents a challenge in actually scaling up our prediction. So we're not able to predict for the entire country. And so for future work, we'd like to explore other ways to collect more examples of sites with diesel-based irrigation systems, and then be able to refine our model and also validate our predictions further. So what does all this mean? We have trained this model. So how can we apply it? One implication of this model could be that it could be very useful for a grid planner, and it could potentially have the implication of stretching out existing capital budgets to provide access to more communities. I'll give a brief example of this. Suppose we actually have a grid planner who has money to provide access to 100 communities, but any added revenue from electrifying diesel irrigation pumps would supplement the budget and provide access to an extra community. So let's take two planners. One has no data from our prediction model. So they have a 20% chance of electrifying diesel pumps if they actually have the original map of where irrigation is happening. And then we have a second grid planner who has a prediction model. This shoots up their chance of electrifying diesel pumps to about 75%. So this means that the first grid planner can only have added budget or revenue to electrify 12 extra communities, and so a total of 112. But with a grid planner with a prediction model where they know with a 75% certainty where to actually find sites with diesel irrigation activity, they would have enough budget to electrify 250 communities. So other policy implications are for the consumers or the electricity consumers with the irrigation pumps. The additional revenue from this anchor load could be used to cross-subsidize the lower income residential customers. So cost-reflective tariffs can be more affordable. We can also see reduced dependency, both at a macro level and micro level, on fossil fuel pumps, which means that then rural smallholder farmers can increase their incomes from avoided fuel and pump maintenance costs, especially if tariffs are more affordable. And just the reduction in dependency on fossil fuels can then enhance the climate action plan of Ethiopia. So thank you for listening. I'll be happy to answer questions during the session.